Hi everyone, today we're going to be talking about Gibbs Free Energy and why a reaction happens. To predict when a reaction happens, we have to talk about the two driving factors, enthalpy and entropy. We know that entropy increases with temperature, and that'll bring us to our second law of thermodynamics. The second law of thermodynamics states that all spontaneous processes in the universe drive it towards more entropy. That's part of the reason why salt dissolves in water. Dissolving creates more entropy than before. The second factor we need to talk about is enthalpy. Whenever you're looking at reactions, they happen because mainly atoms want to move from a higher potential energy state to a lower potential energy state. Enthalpy is sort of an indication of that potential energy. If a reaction is exothermic, it is releasing energy, therefore the atoms and molecules are going to a lower potential energy state. So we now know that the two reaction driving forces are entropy and enthalpy. We want an increase in entropy and we want an exothermic reaction with a decrease in enthalpy. So now let's look at our equation for Gibbs Free Energy. Gibbs Free Energy tells us when a reaction is going to be spontaneous and when it's not going to be spontaneous. And for some reason, Gibbs Free Energy is in kilojoules. When it is negative, the reaction will proceed spontaneously. When it is positive, the reaction will not proceed spontaneously. And when it's at zero, the reaction is at equilibrium, which is a concept we'll talk about later. So our equation is delta G equals delta H minus T delta S, where delta G is Gibbs free energy, delta H is the change in enthalpy, T is the temperature in Kelvin, and delta S is the entropy in joules, and you will have to change that to kilojoules. Now that we know what those are, let's try a practice problem to figure it out. For this question, we're asked about the Haber process, where nitrogen and hydrogen react to make ammonia. We're given the enthalpy and we're given the entropy. We're asked to determine delta G at 25 degrees Celsius. The first thing I see there is a 25 degrees Celsius. We have to convert that to Kelvin. So if we do 25 degrees Celsius plus 273, we get that that temperature is 298 degrees Kelvin. Or not even degrees, just 298 Kelvin. So now let's look at our equation. But there's one more thing I see. Entropy is in joules, and we know that delta G is in kilojoules per mole. So we need to change that to kilojoules. We're now going to make that negative 0.1982 kilojoules per mole. Alright, finally, now we can look at our equation. We know that delta G equals delta H minus T delta S. This equation is very important, so you should really remember it for a lot of different uses, which you'll see in the future. Alright, so first of all, let's plug in our enthalpy. Our process is exothermic, so we have an enthalpy of negative 92.38 kilojoules per mole. Now we have to plug in our entropy term, so it's minus 298 Kelvin times negative 0.1982 kilojoules per mole. Now let's simplify a little bit. We still have this 92.38 kilojoules here, but first of all we have a negative right there and a negative right there. So when they cancel out and they make a positive, and that positive is going to be plus 59.06 kilojoules per mole. Finally, we can calculate our final value for delta G. When we combine those, we get that delta G equal to 33.32 negative kilojoules per mole. And because this value for delta G is negative, we know that this process to make ammonia is a spontaneous process. One more thing you need to know is that delta G is a state function, so you can use the summation equation when given a table of values, just as you can with entropy and enthalpy. Well, that's all I have for you guys today. I hope you guys enjoyed this video, and I hope this video helped you understand what Gibbs free energy is and why it's important. I'll see you guys next week when we talk about gas laws.